You know, we always hear about the incredible promise of quantum computing, that it's going to solve problems we can't even dream of tackling today. But actually building these machines, it's one of the toughest engineering challenges in history. So today we're going to dig into some really fascinating new research that asks a pretty wild question about how we should be building them.
I mean, it sounds completely backward, right? To get more power, you make things smaller and you separate them. But stick with me here, because this really counterintuitive idea might just be the secret weapon against quantum computing's #1 enemy.
Yep, that enemy has a name. It's noise. And to really get why this new solution is so clever, you first have to understand the problem that's been holding the entire field back.
All right, so let's get into it. We're living in what everyone calls the NISQ era. It's a fancy acronym, but it basically just means that our quantum computers are finally getting powerful enough to do some cool stuff, but, and this is a big but, they are unbelievably fragile. They're in this constant, nonstop battle against errors.
Now, this noise we're talking about, it's not like the sound from your headphones. Nope. In quantum computing, noise is any tiny little thing that goes wrong. A stray magnetic field, a tiny fluctuation in temperature, anything that messes with that super delicate quantum state. Think about it like this. A quantum calculation is like a perfectly still, glassy pond. And noise? It's like someone tossing a pebble in. The ripples spread out instantly, wrecking the whole reflection. And here's the kicker. The bigger you build your quantum computer, the bigger the pond, and the more chances there are for those pebbles to get thrown in, until the whole thing just collapses. Okay, so if building one single, giant, super sensitive brain is the problem, what's the alternative? Well, this new research basically says, hey, what if we stop trying to build that one massive processor and instead we start thinking about a whole team of smaller, independent ones?
And this slide, this is where it really clicks. On the one hand, you've got the old way, the monolithic design. It's like trying to build one enormous, insanely complex clock, with a million gears. If just one of those tiny gears gets stuck, the whole thing grinds to a halt. But the new idea, this modular quantum parallel architecture, or MQPA, it's more like having a bunch of simple, separate clocks. If one of them stops working, no big deal. The rest just keep on ticking.
So you're probably wondering, how does this actually work in practice? Well, it uses a classic strategy, divide and conquer. First, you take a massive, gnarly problem, and you break it down into smaller, more manageable chunks. Then, each of these little quantum processors tackles its own piece of the puzzle, all at the same time. And finally, a regular old classical computer comes in at the end to sort of stitch all the individual answers back together to get the final result. Pretty clever, right? Okay, this all sounds great on paper, but does it actually, work? Well, the researchers didn't just guess. They ran some super detailed simulations to put the old monolithic design head-to-head against this new parallel idea. And the results? Whoa, they were pretty stunning. All right, let's look at the actual data here. See that blue line? That's the old school single processor design. Look at how fast its success rate just tanks as the noise gets worse. I mean, it literally falls off a cliff. But now, look at the purple line. That's our new parallel design. It is so much more resilient. It just hangs in there, keeping a really high success rate, even when things get super noisy. And this chart, this just drives the point home. It's the bottom line, right here. That central bar chart shows the performance advantage. And, well, it's not even a contest. The parallel approach, that green bar, just delivers a huge improvement in getting the right answer compared to the standard way of doing things. Let me just throw a number at you. In one of the key tests, the parallel design had a 74.5% greater success rate. Let that sink in. That isn't just a little bit better, that's a total game changer. And when you dig into the details, you see this isn't a fluke. At noise levels that are actually realistic for today's quantum computers, the parallel system was 46% better. And when they cranked the noise way up to simulate really bad conditions, the advantage grew to over 51%. The takeaway here is super clear. The tougher and noisier the environment gets, the more this new approach just pulls ahead. But you know how it is in physics and definitely in computer science. There is no such thing as a free lunch. So to get this incredible resistance to noise, this new parallel architecture has to make a very, very specific trade-off. And the researchers are really upfront about this, which is great. They put it plainly. They're not breaking the laws of physics here. They're not saying that a bunch of tiny 2-qubit computers can magically do everything a big 6-qubit computer can. That's impossible. What they are saying is that for specific, practical problems in the messy, real world we live in, this method just flat out gets you
better answers.
So here's the deal, the big trade-off. On the one hand, you get this absolutely incredible resilience to noise, right? Because any errors are basically trapped inside their own little modules. That's the huge win. But on the other hand, the calculation itself gets a lot longer. It takes somewhere between 7 and 17 times more computational steps to get the job done. That's what we call circuit depth. It's basically just how long the list of instructions is. So you're trading a shorter, error-prone calculation for a much longer one that's way more likely to be correct. And honestly, in this noisy era of quantum computing, that seems like a really, really smart bet to make.
So what does this all mean for the future of quantum computing? Where do we go from here? Well, this research really seems to point towards a much more practical, maybe even achievable path for building machines that are actually useful.
First off, we need to know these results are the real deal. And they are. This chart shows that the researchers ran the experiments 5 different times. And as you can see, the outcome was incredibly consistent every single time. Statistically, the results were just off the chart significant. This isn't a fluke, it's a real, repeatable effect. So ultimately, it really just comes down to using the right tool for the right job. Look, maybe someday, in a perfect, low-noise future, that one giant monolithic brain will be the way to go, especially for problems that need what's called full entanglement, where every single qubit has to be deeply connected to every other one. But for right now, for today, in the messy, noisy reality of the machines we actually have, this parallel architecture seems way better for any problem that you can, break down into smaller pieces. And that leaves us with this one last, really fascinating thought. What if the race to build a useful quantum computer isn't about building one single perfect giant brain? Maybe, just maybe, it's about learning how to be the conductor of an entire army of smaller, smarter, good enough computers, all working together in harmony to solve problems we once thought were impossible.